In this video, we're going to talk about vector fields. I'm going to introduce the big idea, I'm going to show you a bunch of examples of where they come up, and we're going to introduce the terminology to talk about vector fields. Now, I want to begin by imagining that I drop a ball. Now, there was a sort of arrow which said where was the vector going to go when I released it from rest. It went straight down from my perspective. But if you're on the opposite side of the world from me, then the direction your ball travels is very different than the direction that my ball travels. And so what you can sort of imagine is that anywhere that you might be, either on the surface of the Earth or indeed anywhere in the solar system, if you take a ball and release it from rest, there's an arrow. It's the arrow that says that is the direction in which the ball is going to fall due to gravity. That is the idea of a vector field. It is an arrow that tells you what's going to happen at every single spot. Let me give you a different example. This is a standard plot of wind speed. I sure feel like a weather person right now where I'm standing in front of a green screen and I've got a weather map behind me. But nevertheless, what this shows is that at every spot, there is an arrow, and that arrow indicates the wind speed. This happens to be a map at a particular point of time for a tropical cyclone, but it has that same feature of dropping the ball where at every spot, there is an arrow, and the arrow is indicating what is going on at that spot, whether it is a wind speed or whether it is the direction in which the ball would fall due to gravity. Something like this, where you want to give a magnitude and a direction at every point in space, are called vector fields. So with a little bit more precise mathematical terminology, what I might say is that a vector field is just a function from Rn to Rn. It's something with an input domain, so at every point in space, perhaps R2 or R3, then you get an associated output, which is also an R2 or R3. Standard examples would be n equal to 2 or 3. So for example, in 2 dimensions, your function is going to have a 2-dimensional output. It's going to have an I hat and a j hat component. And the standard terminology is we'll put m to signify the function, the m of xy, that's what's going on in the I hat, and n, the function that's going to go on in the j hat. So basically your big function f can be decomposed into this component in the I hat and this component in the j hat. Likewise, it could be 3-dimensional, which would also be very standard, in which case the standard terminology for the 3 component functions are m, n, and p. So for example, in that plot of wind speed that we had before, that was a 2-dimensional plot, and at every location in the xy plane, there was a 2-dimensional vector, and that vector told you the wind speed at a particular point. Wind speed is both a direction and a magnitude. Nevertheless, you could encode that with these functions m and n. And then a lot of the standard terminology from calculus just comes along with these functions. So for example, we might say a vector field is continuous if the m, the n, the p are continuous. Or we might say that a vector field is differentiable if the m, the n, and the p individually are differentiable functions. Now what I want to do is actually draw by hand a particular vector field. I'm going to draw the vector field y in the I hat and minus x in the j hat. And so what I'm going to do is just plug in various values of x and y and see what vectors I get. So for instance, if I take the vector field and I plot it at the point 0, 0, then I'm just going to get the vector 0, 0 out. And so I can represent that by just putting a little dot right at the origin at the location 0, 0. If I come here and do the vector field at the point, say, 1, 0, then by plugging that into the yi hat minus xj hat, then this is going to give me the vector 0 in the I hat and minus 1 in the j hat. So how do I plot this? Well, I first go to the location of 1, 0, which is 1 to the right and 0 down. But then I have to draw a vector, which is 0 to the right and minus 1 down. So I draw the vector that comes straight down and looks a little bit like this. So that is me drawing the vector at the location 1, 0, and the vector itself is the vector 0, minus 1. We could keep on doing these. How about instead I figure out what happens now at, 1, 1 instead. In which case, if I plug it into my formula, then I'm going to get 1 and minus 1. Well, how do I draw this? So for the f of 1, 1, I go up to the location of xy equal to 1, 1. And then I draw a vector which is
one to the right and one down, and it looks like this vector right there. And we could keep doing this as much as we wanted. Why don't we do just one more here and see what happens? I'm going to do the spot that starts right up here. I'll start and do 0, 1. It's always nice to combine zeros and plus or minus 1 is sort of the standard test points. Either way, I put this in, and what it starts with is going to be the y value, which is 1, and then minus the x value, which is 0. And so this is a vector that goes 1 to the right and 0 up. So 1 to the right and 0 up goes there. Now, you could keep doing this. You could keep on adding new points and plot them around. And for example, I'll just do a few of them. I've checked it. You can see that this one's going to go over there. This one's going to go over here. And if you keep doing this, you notice that there's sort of a bit of a sort of circular type pattern occurring here. So this is useful to do for a few points, but it gets a bit tedious, so let's let the computer do the rest.
Okay, so I'm back now, and what I've done is just plotted this with the computer opposed to doing it by hand, and that's totally fine. And indeed, what we get is this sort of circular pattern. Now, when you get a computer to plot a vector field, and by the way, I'm going to link down below some simple plotters so that you could put in different types of vector fields and see what it looks like, there's often choices that are made. So one thing, for example, is that this looks pretty messy because the arrows are sort of overlapping. And so one thing that you might want to do is, instead of having a vector, which we think of as a length and a direction, is keep the direction, but maybe play with the lengths a little bit. So this is, for example, a rescaled version of the same thing. These lengths are not accurate. That is, the length of the vector at some random point, like 2, 3, is not the length of the vector that would be 3i minus 2j. What it's done is it just proportionately scaled everything so that it just looks a little bit prettier and you can see the circular pattern a little bit better. And a lot of plots of vector fields end up having these kind of features. Similarly, from the perspectives of computer graphics, there's a question of density. What I've plotted here is that I've divided the domain, the x's and the y's, by integer values. So at every point, like 1, 0, 2, 0, 1, 1, 2, 1, all with integer values, I've gone and plotted an arrow. But maybe I wanted to see with a bit more density. So now I'm going to double the density. That means I'm going to split up, say, the x-axis not into integer values, but into a half, 1, 1.5, 2, and so on. And so I've just plotted way more arrows. I mean, I could plot even more than this. It would just depend on my density. That's a choice about my computer graphics, not a choice about the underlying vector field. Okay, so this was one. Let's just take one more. This is just one that I think is kind of pretty. It's sine of xy in the I hat and cos of x minus y in the j hat. And as you can see, they just get kind of interesting, and with a little bit of length scaling and density adjustments, you can make these really pretty plots. And so often you play around with these features just to get it to something that you can visualize nicely. The next vector field that we're going to do is the vector field xi hat plus yj hat. And this one, I'd actually encourage you to pause the video and see whether you can quickly sketch it yourself using the methods we've done before. However, if you don't wish to pause and just want to enjoy the show, well, then what it looks like is just this. It sort of looks like a starburst. Here, by the way, I haven't applied any length scaling and I'm using this integer density that I started with. But it kind of looks like the starburst. Basically, at any point, say 1, 1, then the vector, which is also 1, 1, is just sort of pointing straight outwards. And the reason I'm showing this one is if you can sort of see that starburst behavior that's happening with this vector field, I can do the same thing in 3 dimensions. This is what it looks like. It's a 3-dimensional plot now, and now this is the vector field xi hat, yj hat, and zk hat. So it's got 3 components. And then what I get is a 3-dimensional vector at every point in 3 dimensions. And again, it kind of looks like this burst sticking out from the origin. So indeed, we can plot 2-dimensional or 3-dimensional vector fields. And again, I'll put a link down below to a plotter for a 3-dimensional vector field if you want to play around with changing the component functions away from, say, the x, y, and z that I have here. Now, while we're on that theme of how you can play around with the computer graphics a little bit to plot these, I want to go back to that original wind speed vector field that we saw at the beginning of the video. Because notice it's not just the fact that at every point in the xy plane, there's some 2-dimensional vector that tells you the magnitude and direction of the wind speed. There's also color in this plot. So So what's going on with the color here? Well, the color is a way to signify easily, quickly, visually, what the magnitude is. So in this plot, the sort of whiter, pinker tones are ones that have faster wind speeds, while going back from reds to orange to yellows to greens to blues are progressively slower and slower wind speeds. So you can sort of see that in the middle, this is where that cyclone is going, where it's got the fastest speeds going on there in the middle. So you can either color code the background, which is what's done in this plot, or sometimes you might just even go and color code the vectors themselves. And this is a really good way to be able to visually and quickly see what's going on as well. Now, previously in single or multivariable calculus, you'd often have the domain either be a line or perhaps a plane, and then the codomain, the sort of the target of the function, would be some height above that line or above that plane. And those were the things that we could graph nicely. However, for a vector field, even with n equal to 2, so that's a two-dimensional input and a two-dimensional output, a graph would be four-dimensional and therefore is hard to graph in that normal way. However, as we've seen in this video, we've had this wonderful new way to visualize things where at every point in either the plane or in space, you just draw a vector, you draw an arrow, and that signifies what's going to be going on in the output at that particular input spot.